All right, today we're going to be looking at section 7.3, log functions and their properties. I'm just going to start out with giving you a few notes instead of going through the text and doing an overview. I'm just going to give you a few points to be mindful of. So I will start out with a log. So log is what we call a logarithm. It's given some base, so there'll be some number that's debased. We'll be evaluating some other value. I'll just put a, and then it's equal to x, or they may put y, but it doesn't matter. Okay, so this is just a generic log. If we do not give you a base, if I just write log, the base is understood to be a 10. Okay, so I can say log base 10 of a, and that's the same thing as if I just wrote log of a. Okay, so understand, if you see log, it's understood to have a base 10 unless they give you something different. So now we will go from log to exponential. So this is one of the important things, being able to write a logarithm as an exponential. So basically what happens is if you have a log, some base b evaluated at a equal to x, you're going to take your base of your exponent, and that is going to become the base, take the base of your log, and that's going to become the base of your exponent. Once you remove that, the log is no longer there. So the b comes over and you end up with a equals b to the x power. And then it's the same thing. Going backwards, you would just remove the base of the exponent and put it over here, and it will become the base of your log. Okay, so you want to be able to go forward and backwards. So just for example, if I had, let's say, 10 squared, and I had that equal to 100. The way this looks in terms of log, since this was the base, it's going to move over here and become the base of the log. So I would have 2 equals log base 10, or it could be understood evaluated at 100. So whatever is by itself, that's what's in the parentheses with the log. And I will actually go ahead and open the calculator and just show you that that's a true equation. Logs are very much related to exponentials and radicals. So if I turn this on, and then here's the log button. So if I do log, and it's understood to be a base 10, and I put 100 in here, and then I hit enter, it gives me 2. Log of 100 is equal to 2 in base 10. So it does show you that it works. Now, this is, I guess, very important because this is the first problem that we're looking at. Also, you have what we call natural log. Okay, natural log is denoted by ln, and it has a base of e. Okay, so I can say ln of a. So you can do the same thing as far as converting this to exponential form. Whatever your base was, it becomes the base of your exponent. And so this would be a equals e to the x power. If we wrote this natural log, if we wrote this natural log in terms of exponential form. So that's important. We're going to be doing log from exponential, and then exponential to log form, back and forth. You will be asked to find the domain of log, and what you need to be mindful of is that log cannot take negative inputs. Okay, so whenever you have a log function, let's just say log of, let's say x plus 2, doesn't matter what your base is, okay? Only thing that matters is what you're evaluating. Whatever is inside the log has to be positive. So you take what's inside, and I'm going to say D for domain. This part has to be greater than 0. So only what's inside has to be greater than 0. And then solving, you would subtract 2. That will divide out or cancel out, and that will leave you x has to be greater than -2. So any x value that you pick greater than -2 will work as far as this whole thing needing to be positive. And then if you want to put that in interval notation, you would do -2 up to infinity. Okay, so both of those are essentially the same. So you need to know log and be familiar with their understood base. Log has a base of 10. Natural log has a base of e. So just again, I can write ln, and I can just evaluate it at a. And you need to understand that it has an understood base of e always. And most of the time they will not write it. And then whatever's inside, you just set that greater than 0. That's the rule. Set it greater than 0 to find the domain. So this is the first part. Being able to write a log in exponential form, and then being able to find the domain. We will also be asked to graph some log functions. Okay. So you can do it a couple of ways. You can use graphing calculator, or you can use properties of transformations that we've talked about. So let me go back to our content. And not in there. I don't see the graphing in there. Yeah, here we go. In Module 2, Parent Functions. You can also find this online somewhere if you just search Parent Functions. So exponential curves up to the right. We talked about exponential growth and decay. Now, natural log or log, it hugs the y-axis. It's just a mirror image. These are inverses. It hugs this y-axis and curves and crosses at 1. So this is if the b value, the base, is greater than 1. Okay, if it was less than 1, it would just flip and come across. It would come from the top going down. So we'll talk about some of those properties, but just being familiar with those, and then we will just do horizontal shifts and vertical shifts, and then adjust from there. But again, you can always graph them with your graphing calculator and also see, or just plug in some numbers and then plot some dots. I'll try to show you both those methods, but for the most part, if you're familiar with, let me scoot this over. If you're familiar with log, I guess I can't go over. Can't scroll. Let me see. Yeah, here we go. If you're familiar with the general shape of the log graph, that's going to help you out. So we will do some graphing, and then we will also do some solving. So again, I recommend that power table that we used with exponential. I like this output right here. We're going to be solving some logs, and this power table will be helpful being able to rewrite those bases. So that's going to come in handy whenever we're rewriting logs in terms of exponential and vice versa, which you'll see that here shortly. But one of the things that may help you is remembering that each operation that we use in math has an opposite. So, and maybe this will help you with rewriting logs as exponential form. So you know the opposite of addition is subtraction. Okay, the opposite of multiplication is division. And then when we get to powers, so let's say I had an x squared, okay, the opposite of that would be square root. And now we're here to these logs. You got some log base b. The opposite of that will be doing base b and raising it, or just raising everything to the b power, whatever that base is. So log b. So the way you cancel out log is using that base as an exponent and vice versa. So if I had, let's just say 6, and then I had a log base 6, and then I was evaluating that at, let's just say 4. The 6 as an exponent and the 6 as a base will cancel each other out, and then that would just leave you with 4. Okay. How is that related to writing a log in exponential form? If you think about that, it cancels out. So let's say I have log base 10, and I'm evaluating that at, let's just say 1,000. And that should be equal to 3. So remember how I was saying that you just move the base over. So take this base, move it over, and then you have that answer. So that would be the same thing as saying 1,000 equals 10 to the third power. Well, think about raising both sides to the base of 10 power. So 10, and I write log base 10, evaluated at 1,000. And then over here, I would do the same thing to this side. So just give it a base of 10. So I added base of 10 to both. We're going to get this same thing here. So the 10 and the base 10 here cancel each other out, so that whole log gets canceled out. And then you're left with 1,000 equals 10 cubed. So that's just a property of logs that will cancel each other out. You will see that. And the same thing works with natural log. So if I had ln of e, and I had some value, just say 5, and then I was to raise it to the e power, okay, or let e be the base and this be my power, ln of e and e will cancel each other out, and you would just be left with 5. Now, this works both ways. So here's what I mean when I say both ways. I could have e as the base, or I could be evaluating at e, and it will still cancel out. So that means ln, understood base of e, whether I write it there or not, and then let's say I put e to the 5th power. So the ln e will cancel out this e, and the whole thing will cancel out, and I'll be left with 5. And it also works with log, log. It has a base of 10. So if I was to put 10, if I was to put a 10 here, and let's say raise it to the 2nd power, log base 10 and 10, those cancel each other out, and you would just be left with 2. So it works if it's the base and this is your exponent, and it also works if this is your log and you're evaluating the base inside. So that's just kind of like the property of simplifying or canceling out with logs. So just overall, just to give you a general overview of what we're going to be looking at, we're going to be taking log expressions, and we're going to be writing them in exponential form and also going backwards. So they may give you an exponential form, and you're going to convert it to log form. You are going to be doing that with both log and natural log. We're going to be solving some, which I hadn't got to any solving yet. We will try to find the domain of log functions. We will use the property of log to cancel out and rewrite them. So understand that if you raise log to the base of whatever the base of that log is, it will cancel out. And it also does the same thing if you take the log with its base and evaluate it at its base, it will cancel out. And then beyond that, we will do some graphing and some evaluating. But overall, that's going to be what we see here. So let's actually just start doing some examples.